So just a reminder, next week at this time, the test number 1 will begin. And incidentally, next week, the test will appear exactly at 5 o'clock Eastern Daylight Time. So everybody, you better log in, and I will myself also be logged in about 10 minutes or 5 minutes before, in order to be ready, because whatever instructions I may have, last minute instructions, it will be given before 5. And then when exam is on Blackboard, not on Wiley, but the questions are sort of like what you have been doing in your exercises, homework. So, but it is not on Wiley, it is on Blackboard, and I will give you the link, session link, so that you can get on, and it will be on the content page of Blackboard, and it will appear. And when it appears, its clock will start ticking, and it is supposed to have 75 minutes. And when you do it, for each question, they will appear one at a time, no backtracking, and there will be, I think, 15 questions, but the 15 questions will be in blocks. And they call it, Blackboard calls it random blocks, so that this block may appear, as the first block in yours, but it may be the third block in somebody else's. And within each block, 1, 2, 3, 4, whatever the number of questions in that, will also appear in a random order. I mean, Blackboard is good at randomizing everything. But for each random block, I will have a sort of a notice to say, this random block has, let's say, 3 questions. And it could be maybe all 3 multiple answers, which is basically multiple choice, but with formula. And I am good at confusing you, and I will have an equation which is the correct one, but then I will put in a minus sign here, put in a factor of 2 here, invert the orders, and so on. So you just have to be careful to know exactly what. Now, somebody had a question. You want to say it out loud?
Will the test be more mathematical, conceptual, or both?
It's conceptual, but it will be formula based, so that I can tell that you got the right concept. Because if it is something involving, I don't know, Coulomb's law, and instead you were using magnetic force. I mean, although magnetism is not included in this test number 1, but what I'm saying is, if you get the right concept, then you know which formulas are involved. You got it? Yeah. And as I said, the Blackboard randomizes it. If it were me, I would say part A first, then part B, then part C. But somehow Blackboard doesn't know what I'm trying to tell them, and there's no way. I keep asking around. Nobody knows how to fix Blackboard for that. So what I would have called part A, part B, part C, it may come out to you as part B first, and then part C, and then part A. That's why I put down there to tell you there are 3 questions. Maybe it is 1 multiple answer, 2 calculated formulas, or 2 multiple answers, 2 calculated formulas, so that you know. And they are in the same topic, the same concept. But for each one, I am just asking a different aspect of that question or that concept of that situation. All right, so just for each question, don't immediately plunge in. My advice is I have allotted something like 5 minutes for each question. So you read it and then read it carefully, because the wording, it can be very tricky sometimes. Somebody, can you say out loud what you have? Somebody had a
Yes, sir.
question.
Do we have to memorize the formulas or will they be
No,
given on the question?
no. I will not give the formulas in the question. You have your laptop. Now, somebody asked whether the college will lend you laptops. I haven't got the answer for that yet. Somewhere, I don't know. But you have your own laptop. Bring it. By the way, it will be live. You will be in person. I think it should be MR3. Although, again, I have to wait for the department to get in touch with the registrar to then say which room has been set aside for 204 at 5 o'clock on Wednesday. But I think it is Marshak room 3. And there will be, how do we keep track of what? So let me finish. So you will be live and there will be proctors there. And the role of the proctor is just to be sure that there is no chatting, there is no passing around of sheets from one to your friend or to your neighbor and so on, so that you all are separated. Will the room have plenty of? I think so. I think so. I think so. There will be plugs for each seat. They have already a plug. I think so. I mean, we'll see how things work out. But as I remember, for the spring when it was also locked down, there was no issue with not having charges. And now, when you have, then there was a question of what happens when you now, let's say, in that random block. Somebody was asking. I didn't catch that. When you have a question, unmute yourself and just ask, because then I know.
Sorry, Professor. Are we going to be taking the exam in the same room as the lab, Marshak 407 North?
No, it would not be in the lab. It will be in a bigger room, because lab cannot take 75 people or 72 people. So it has to be in a big room like Marshak 3, room 3 downstairs. And it's big enough that you can be separated. Okay? And now let me address this issue of part A, part B, part C not being in the order in which I would have, insisted, but Blackboard cannot accommodate my request. So part A, part B, part C may come out in a slightly different order, but they are all focused on the same situation. And so when you do yours, you may be doing part C. It is the same situation, but now maybe I'm asking for what is the current, or maybe I'm asking what is the resistance, but it's the same situation. You know the set of formulas that involve it. And so you then say, okay, I now work on part C because it came out first. And whatever the information, is given as I and a V and a P and a Q and a C and so on. And then you say, oh, I know it is this formula and I use it. And then part A comes around and says, well, I have this and I'm told that the voltage is blah, blah, blah. What is the current? So you know yourself what concept it was, and you know which formula to use, which would have been for part A, it is this formula. For part B, it would have been this other way of writing the same formula, and so on. So you are warned ahead of time. And for each part, there will be a description, and it's basically the same description, that it is some guy riding on a horse and he's going galloping at such and such, and now he suddenly saw his girlfriend, and then he did this and he did that. It would be the same description, but the question that is asked is a different aspect of that same situation. Are you okay with this now? I'm trying to explain the context of this random block. Can somebody read what you...
They said, since we are able to use our notes, do you care whether or not they're on a laptop, iPad, or written out?
Yeah, you can have your own written out, but you cannot pass your sheet on to your friend next door, in your neighbor. That's what the proctor is there for. Proctor is there to be sure that you're not whispering to one another, you're not passing your sheet to another, but you have your laptop, you have all access to all the notes that you have. You have access to the ebook, you have access to all the PowerPoint. Everything is in your laptop, but you need to sort it out for yourself. And that's why my advice is, I have allotted 5 minutes for each question. Don't immediately plunge in. Just because you see a horse, then you say, it must be to do with such and such. You read it, get the concept, like what are they asking? What did they tell us? And you then do it. Somebody had a question again. Can somebody say it out loud?
I said my notes are in my notebook. Can we bring our notebooks too?
Yeah. You can bring everything that you would if you had been online answering it anyway, but you cannot pass your notebook or throw your notebook to your friend in the next aisle. No such thing. The proctor makes sure that. And also, during the time of the test, I will be online and you can chat with me. You have to, of course, mute your phone, all the mics. You can chat and say, Professor Chang, there's this thing involving the horse, and and then I will know what it is about, and I can maybe just tell you, be careful of the units, or I can tell you, no, it is this. I will not, of course, be able to tell you, yes, you used equation number 625 from your chapter 6. I will not tell you things like that, but I will at least help clarify what is the question that is posed. In other words, you can ask me questions about the problems. I will be on Blackboard, right? That's what I'm saying. I will be on Blackboard, but you can chat with me by chat, but not by clicking on and say, Professor, what is this? Because then you'll be disturbing everybody else. But if there is indeed some mistake on my part, then I may in fact turn on the mic and tell everybody, sorry everybody, for any question involving blah blah blah, involving the horse, it is actually colored red, not blue, or it actually is colored black, and so on. I will have to announce it, but apart from that, the proctor does nothing than to be sure that you are not passing notes to one another, talking to one another, and sharing your notes. Any other questions?
Yes, Professor. I just asked in the chat at the beginning, like before class started for the semester, I sent you my accommodation memo. I just wanted to make sure that you got it as it pertains to our exam.
To accommodate? Oh yeah, I mean that I have to get the this accommodation center to tell me exactly how. whether they have proctors available. You can email me for those with those other issues. You can email me. Okay. Any other?
Okay, I did. I just wasn't sure if you got it. I never got a response back, so I wanted to make sure it was actually received.
Yeah, no, but I'm trying to find out from those people exactly what they are able to do, because for the final it would be 2 hours and 15 minutes, and they need to have proctors that last through the night. But anyway, that's a separate issue. Any other question?
Will you let us know if it's MR3?
Yeah, I will let you. Well, this next, I hopefully by Monday I will be able to tell you it is MR3. You know, the administration, you send them, they don't answer because they say they have millions of people sending in requests. So, but I will sort it out, and I have already been asking our department secretary to sort it out with the registrar. And I think it is MR3, but just to be absolutely sure that there's no confusion. Any other questions? Okay. Yeah. Will that? Oh yes, there will be lecture after the exam. The exam is until from 5 to 6:15. Yes. Yeah. From 5 to 6:15, and then after a 5-minute break, I'll resume online. Even though you are there in person, I am here, you know, at home. We can resume, since you already have access to the Wi-Fi. We can resume online at after a 5-minute break. Okay, so now let's go on, because, and incidentally, magnetism will not be on the test. So, but magnetism happens to be a very big chapter, and so we have to go over it slowly. Can we stay? Yeah, you can stay in MR3 to take to continue with the online course. Okay, so now, any other questions? Okay. Oh, somebody asked about recitation. The labs are mandatory. You must take the lab and do the lab and send in the lab report. Recitation is for the people who feel that it would help to have somebody explain, and you can ask questions about what is this Coulomb law, what is this electric field, what's this capacitance, in order to help you get the concept. And if you feel that you're already good enough and you don't show up, that's okay. I tell the TAs that they are not going to punish you and say, oh, you didn't show up at all of my recitation sections, therefore I give you a 0 for the whole lab report for the semester. I say no such thing. All that matters is that you submit the lab report for every lab. Okay? What was this week's yeah, I know. I have difficulty sometimes getting a response from the TA, but anyway, I have already told them before, so that's okay. 19 homework. I don't remember. When was the? Was it due today? No, October 1st. Or today? Yeah, maybe afterwards I will extend it to what is today? No, I thought I set it for October 1st. No. Yeah, so you still have one more day. So no, October 1st is Friday. Well, I let me think about that, whether or not to be so gracious to you just because you can. But actually, if it's past due, it helps you because then you can look at all of the answers and hints and be able to be stronger. All right. Anyway, let me, if you let, I will not now say yes, yes, no, no, but maybe, maybe, yeah. All right, let's come back to this because it's any other questions? Oh, did I already say because this exam is a format that is sort of maybe different from what you have been used to, the performance, the score, the what the your raw score, the raw score would have been 150 because each question is 10 points automatically. But I will have a grader look over it because, as I said, Blackboard is very fussy. When it says you should give two significant figures, and the answer was let's say 1920, joules, and you wrote down 1920 joules when the thing says two significant figures, Blackboard will say wrong, but the grader will say, well, 1920 means you have three significant figures. It is still okay relative to 1900, which is what Blackboard would, even though the question already said two significant figures. So the grader will give you partial credit, maybe 7 points instead of 10 points. And so the grader will be going over Blackboard. But whatever it is, in the end, the average raw score, let's say, is, I don't know, 110 out of 150. I don't know. But okay, let's say 100 out of 150 because it's so difficult. People don't know and people get all tense. If let's say it's 100 and you didn't get 100, I'm so sorry to hear you only got 40. But the next time around, you have been doing a lot more of the exercises. You've been attending all the recitation sections and you have been doing a lot more exercises. And for test number 2, where the average raw score was 100, you got 120 compared with your original 40. I would put down a ratio R that says that you actually got 120 over 40. You really did 3 times, right? You really did do the work in getting better understanding. So at the end of the semester, whatever's the curve that I would use for everybody, if at the end of the semester the average raw score comes out to be B plus, and then I say, hey, you actually, from the first test to the second test, you went like this up 3 times, then instead of B plus, I give you A minus. I may even give you an A. That is how you get extra credit. You don't come to me and say, oh, professor, what can I do to get extra credit? Can I do extra homework in order to get extra credit? I say no. All that matters is your performance on the exams, on the test 1, test 2, test 3. Okay? So I may have said it before, but I want to say it again because I want to encourage each one of you to actually be good with concept and then know what formulas are involved in that concept, and then spend time 5 minutes before each question before you plunge into it. And 5 minutes is actually more than enough time to do. Okay, I think we have spent too much time on that. But now I want to recall this aspect of the motion of charged particle in a magnetic field. If I have first, and charged particle that was coming in, and it came into a region where there was an electric field, and the electric field is, between this plus charge plate plate that is plus charge to a negative charge. Then the electric field is this direction. Then the charge particle coming in would now go into a circle, but it is circle in the same horizontal plane, right? Because there is now a force that causes it to. It was coming this way. Now it will go in that. It has a force on it in this direction. For a F equal to QE, for a charged particle in the magnetic field, something different. The thing that is different is because the force on a charged particle is not like the force due to electric field. The force on a charged particle due to magnetic field depends on the velocity of this guy coming in. And when it came in this way and the magnetic field was pointing in this direction, you have V cross B, and the force is out of the plane. Let's say this is horizontal plane. It's out of the plane. And so it now begins to spiral. And I have downloaded, a picture. This magnetic field is pointing upward. Let's say because I put my north pole here and south pole up there. And I now have an electron. Well, electron has negative charge. And what happens is, if I now apply V cross B, I don't know if you can see V here and B. V cross B, the force V cross B would have caused the force to go outward, but because the electron is negative charge, it's inward. So the electron goes around in a circle. All right. So this is the key aspect, the key difference between a charged particle in the presence of electric field versus magnetic field. A charged particle in an electric field is either attracted or repelled. Bye-bye. Or you come meet each other. Instead, the charged particle, when it's coming into a magnetic field, gets trapped. It gets into a spiral. It gets trapped. And this is the picture that I needed to, and I downloaded it from my other course. Here you have this, as I said, this is a cosmic ray from the sun, and it came and hit the Earth. And as it's coming in, the Earth has a magnetic field. This charged particle, V, which is cosmic ray are mostly protons coming in. They then get into a spiral. They get trapped by this magnetic field, and they just keep spiraling. They keep spiraling. And now, okay, this is another picture of the same. You have this X means that the magnetic field is going into the board, right? And I have V cross B, but V cross B would have been outward, but because the electron is negative, it's then inward, and it goes in a circle, and that's how it got trapped. And now, the Earth's magnetic field is like the Earth has a magnet. And when we call the North Pole, it's actually the South Pole of the Earth's magnet is opposite. It's South Pole here, North Pole here, and the magnetic fields, they go out from the South Pole, geographic South Pole, and curves around to our geographic North Pole. So these are now the magnetic fields around the Earth, and they are hugging the Earth. And the strength of the magnetic field is not strong. It's a third of a Gauss. And as we already complained, the engineers, all the electrical engineers, they don't respect Gauss because Gauss is a mathematician. They respect Tesla, and so they measure all the magnetic field in Tesla. And 1 Tesla is 10 to the 4 Gauss, 10,000 Gauss. But the Earth magnetic field is not strong, and it is actually good that it's not strong. Otherwise, we will all be a little bit groggy. So there is this 1/3 of a Gauss hugging the Earth around here. And now when you have these cosmic rays, they are coming from the sun. They didn't know that the Earth has a magnetic field. They are coming all over because the sun, gives off these solar flares, and they are flying all over space. Well, some of them, when they come, they get trapped. And they get trapped, and now they will have to go towards the Earth's North Pole. Or if they get trapped on this side, then they go down into the Earth's South Pole. And when they are trapped and they are coming down, the cosmic rays, they are protons, they will be banging against all the molecules, the oxygens, the nitrogens. They will be banging the atmospheric molecules, right? And when they bang, there will be light emitted. And later on in 204, we will learn about this emission of light. Or maybe it is in 208 when they, or 209. But anyway, you can kind of sense that if my protons, these cosmic rays, they are slamming against the oxygen and the nitrogen, the air molecules, there will be emission of light. Well, the emission of light is this. You can see, it's like, as I mentioned last time, when you see it, it's live. It is not like that's the thing, fixed. Instead, it is pulsating, It's like there's this green, and it's like actually like a flame. It's like a flame, it's like hell's fire. I don't know. It depends on how you want to interpret it. But it is really something that when you see it, you say, whew. And what happens is, these are all the cosmic rays that are now crashing in to the North Pole or to the South Pole, instead of crashing it into you or me. The Earth's magnetic field of only 1/3 of a Gauss has protected us from the kind of cosmic rays. Because when there's a solar flare and it is coming down, and if you have these cosmic rays knocking against your head will have problems. All right. So I just wanted to end with this thing, because this is called borealis because it's in the north side. I think aurora, I don't know, in the south they call it something else. Aurora something borealis, I don't know, australis or something. So, but this is what it is in the north, in our northern hemisphere. Now, the other application, which we kind of already mentioned, but it's good to again emphasize the concept, it is this thing about velocity. If I have, they call it a velocity selector. What do they mean? If I have a charged particle, positive charge, it has velocity v, and is coming into a region where the magnetic field is into the board, or they say into the paper, is into the board, right? Then V cross B, because I am going this way, V cross B would have been an upward force. Would have been an upward force, but I want to keep it going in this direction. How would I do it? What I do is I now put an electric field. I put an electric field, and I put an electric field such that there is now an electric force on my charge. But the electric force on my charge depends on the direction of my electric field. Since this one is V cross B, so it is upward, I would now put the electric field to be pointing downward, so that this is plus, this is minus, and then it will net force equal to 0. Well, no, you can do it here by itself. What you want is that the force be equal to 0, so therefore you want E to be opposite to V cross B. And this E is up to you. You say, oh, you came in with a velocity which is 10 meters per second, and the magnetic field is so many Teslas. We have to use Tesla units for this. If we use Tesla units, then it is so many meters per second, and this Tesla, then I will now use a magnetic field which is so many volt per meter. Again, in the metric system international units, it would be volts per meter, and I will now put it such that it is opposite, negative of this. And since this is designed such that only for this particular velocity the net force is 0, I have therefore selected it. Namely, only the one that I have designed it for, because I have put the electric field of just the right strength, only those will go straight through. The others, oh, it could be either it's not enough, it goes up, or it is more than enough, it goes down. So this is what they call a velocity selector. Now, it is up to the engineers to sort of figure it out. For you and me, the concept is that you are able to, in fact, select, given your V, given your magnetic field, that you can now say, I know what electric field I need to apply in order that the net force be 0 and my charge with a given V will now go through. And it doesn't matter what is Q, whether this is 5 coulombs or 3.5 microcoulombs or whatever, doesn't matter. So long as they have that particular V that you designed it for, it will select that one and only let that one go through. All right, is this clear? The concept that is involved? Yeah, okay. So now, I mean, we already did that, but I just want to keep knocking into our own head, right? And now there's another aspect, and that is the magnetic force, as we said, is Q V cross B, and it is now for a positive charge. If you have the magnetic field into the board, and it is over here pointing to my right, then V cross B would give me a force that is upward. But when it is up here, it is now going in this direction. Therefore, the force V cross B is downward, and this is then the centripetal force. Because the velocity, it is a centripetal force, so the magnitude of this velocity remains unchanged, and it is going around in the circle. So you can now actually figure out the radius of this circle. If it is going in a centripetal in a circle, and since you know the magnitude of your centripetal force, because the thing that supplies the centripetal force is this V cross B, QV cross B. And because that is the source of the centripetal force, and you know that that must be mv squared over r, you can, and you know your V, you can therefore figure out the R. All right, so now that this is the exercise here, right? You say, well, I know it had a given velocity v, and because I already let it go through a magnet, and the magnet is north on this side, south on the opposite side of my laptop screen, so that the magnetic field is from north to south and is into the board, then there will be a force which is upward, and that is supplying the centripetal force needed for my charged particle to go in a circle. And I can now say, well, I know the force is QVB, because V is this way, B is into the board, and this is exactly 90 degrees, so it is QVB mv squared over r. Therefore, I now can figure out that for a charged particle of Q, of charge Q, that when it has been sent into this region with a given V, it will be trapped. It will be trapped. If you send it in with a certain V, it will be trapped, and it will be trapped into one whose circle radius is mv over qb. Whatever is your B may be very weak. If your B is very weak, oh, then the arc, the radius is very long. So that here I was, coming along from the sun. I didn't know that you have a magnetic field, and now I came in to the region near the Earth, and then whoops, there is a magnetic field. And then what happens? I get brought into a radius, where my radius now is my charge Q, and my B, whatever is my your magnetic field. And this could be, maybe radius. So it is a long, a big arc. All right. Can you hear? Can you see? Is there a problem with the internet? Right. You can see, right? So it's a big arc. But now, as I am going through and I knock against the oxygen and the nitrogen and so on, I begin to lose my speed. You got the idea? I begin to lose my speed. So as I lose my speed, my radius gets smaller. You know what I'm doing, right? I first came in, and then I got trapped by your weak Earth's magnetic field. It's, after all, only a third of a Gauss, which is, very, very small in terms of the units of the Tesla, the engineering units. So the radius is big. I don't know, let's say 50 miles, 100 miles. But then as I am now in the upper atmosphere, hitting and knocking against your, silly oxygen and ozone and all the other things that are in the atmosphere, I'm losing my speed. But if I lose my speed, my radius gets smaller. And what happens is, then I really am spiraling and actually knocking against more people, right? And so that's this aurora borealis. But the key concept we have here is that in a constant magnetic field, a charged particle moving with a certain velocity will be trapped in a circle whose radius is mv over qb. All right, now we don't have to talk about the cloud bubble chamber because you're not high energy physicists, so we'll leave it out. But it's that same concept. But we will deal with this one because, as I already mentioned last time, the people who study radioactivity, radioactive, at first, when there was radioactivity, people didn't know what was exactly in the radioactivity. All they know is there's a radioactive source. There is a lot of things coming out, and it took a while to sort it out. And the way it was sorted out was by way of this formula. Because what happens is you now say, all right, I let this radioactive source now come through here. I have a window. I put my radioactive source and I put a window so that over here, all these radioactive guys, whatever they are, they'll be coming out. If they were over here, they would not come out through here. So I have blocked it out. So these are the radioactive guys. I don't know what is their velocity. I don't know what is their mass. I don't even know what they are, but they have charge. If they have charge, then I know, if they have charge, I know that they will be in a circle whose radius depends on their m and their v divided by the e and the b. And now I can now figure out, because when this now comes out, there will be some that will come over here. There will be some that go over there. There will be some that go this way. Those that come this way are positive charge. Those that come that way are negative charge. You follow? Because V cross B, Q V cross B. So here it is, if it is positive charge, they will be having a circle in this side of it. If they were negative charge, they will be on this side of this magnet. And if they are on this side, I will now look at those that fall into this detector. Those that fall into this detector will have the MV over QB equal to what I have measured. I said, I have purposely put this to be, 1.5 meters away. Then only those whose momentum, MV, over the charge, E, times the given magnetic field that I know, and I can therefore now sort out and say, those that fall into here, that in this radioactive decay, that it is what they call alpha particles, that there are these particles, they all have a charge which is, alpha particle is a charge 2. So I know that they are charged 2, and I know therefore their mass, because I can figure out their momentum by the way they impact. And so this now says you can actually figure out the mass if you have already figured out the charge, and you can also figure out the charge by putting an electric field, remember, to sort it out. So you can therefore then say, out of this radioactive, there is alpha particles, and the alpha particle will have a mass, which is from your R that you have measured. You can know what is that it is alpha particle. And very interesting, when they first did it, they didn't know. They say there are some particles that go that way, so they call it beta. So there's this alpha ray for those that are positive, and there are the beta ray, and later on they discovered beta was actually electrons. So the language of radioactivity, where you have alpha, which correspond in the end to alpha particles, beta that corresponds to electrons, and then there are those that just simply go up and they don't even come around. They call those gamma ray. And what we now know is gamma rays are basically light of a high frequency. And this is what we call gamma ray. And there is a lot of gamma rays that are around in the universe because you have a lot of stars that are emitting. So that's how the language of alpha, beta, gamma ray. Anyway, it is application of this basic formula, R equal to mv over qb. Don't worry about this. And then we also had this. I purposely put a sort of a loop, a current loop, and I put it in between, or hang it over here, in between magnetic north and south pole, and I send a current through. Now, if I send a current through here, and the magnetic field is downward, then V cross B will give me a force that is this way. Therefore, since the hinge is here, what happens is when I turn on the battery, when I turn on the current, this thing will now tilt upward. And I could indeed do it such that when it comes up here, I turn the current around and it will then come right back. And this thing about a current coil or a current loop is what we will be doing basically the rest of this chapter. All right. So first we were just simply talking about a free charge and it was sailing across the atmosphere and it got trapped. But for the rest of the chapter, we will be then focused on, I would like to know what are the properties on a current coil or a current loop in the presence of a magnetic field. Okay, so now we want to go more into a wire, because to have a loop, you have to have a wire. You want to first have a wire, and now you have a wire that carries a current. Call it I is the current, is so many amps, and this wire has a length of wire of length L, and you put it in the presence of a magnetic field here. And now again, you would like to say, what is the force on this wire now? Previously, we had well, F equal to QV cross B. But now inside this wire are the charges, and they will be now carrying QVB sine theta, but you now express it in terms of Q per unit time times V times that time interval, because QVB, you can re-express it as the amount of charge going through per unit time times V delta T. But delta Q delta T is what we have already called I, the current, ampere, so many amps, so many coulomb per second is so many amps. So we have already called this I, but now this is the distance that the charge moved in a given time t, and it is V delta T, but that is the length. So we can now re-express this Q V cross B in terms of I L cross B. I is a vector in the direction of the current, L is just the length, and B is, of course, the magnetic field in these Tesla units. And now this is now the force law. From Q F equal to Q V cross B, which is focusing on a given charge, whatever is the charge doing, with whatever velocity, we now begin to talk in terms of a wire. And if we talk in terms of a wire, we would then say, okay, this wire carries a certain current, and the length of this wire happens to be L, and the force on this wire in the presence of magnetic field is now upward. is now upward, and this is the amount, magnitude, ILB sine theta. Are you okay with this? We are going from focusing on a single charge, whatever is the velocity, now to a collection of charges that are moving in a wire, and they all have to move in the wire in the direction of the length of the wire. Is this okay? No comments?
Just to be clear, the angle theta is the angle between the wire and the direction of the magnetic field.
Right, right. Because this L cross B. And right now, this is at this a certain angle. Later on, they'll say, "Ooh, it is maximum when theta is 90 degrees." Because if it is like this, for example, it's good observation. If my wire is oriented such that it's directly parallel to B, would there be any force on me? Remember V cross B? If my theta is in fact happens to be 0, so that my wire is oriented exactly parallel to whatever is your magnetic field, would there be a force on my wire? No. So that therefore it makes a difference. My wire, its orientation to your magnetic field, it makes a difference. It would be maximum force on me if I have my wire in this direction, whereas if my wire is oriented exactly parallel to you, I say there's no force. I mean, we are beginning to get into a wire, and then we will be talking about a coil, a wire, a current loop, and it is important to get this sort of vectorial sense of the law acting on the wire and therefore on the loop in the presence of an external magnetic field. Okay, any questions or comments? I hope I'm helping you to focus on the concept. And now, there's a very interesting application, which the book does. And at first, when I read it, I say, "Ooh, I didn't know." And actually, I didn't know. But they say, supposing you have a speaker, like you have your whatever is your radio thing that you have, and you now want to have the, after all, like for example, on the laptop and this, you have a speaker, right? How does the speaker transmit the sound? Well, of course, we learn from, what was it, chapter 16 or something, the sound, that it is because there is a vibration, right? You have a speaker, and what the speaker is doing is it is vibrating, compressing the air, decompression, compressing the air, decompression, and it is a sound wave that come from the speaker that come to my ear, right? Do you remember that from chapter 16, I think? Yes. You better know that, right? So now here is a very interesting application that you need a magnet in order to attract a coil, because you have a wire down here, right? You have, after all, your speaker has a wire there, and therefore now there's a wire wrapped around this speaker, and then because there is a magnetic field, when you pass a current through it, the magnetic field now exerts a force on this guy and kicks it out. But now it is not the speaker, the signal from the laptop. It's not always that way. It is sort of like, I'm, hey, I'm talking, and my voice, my sound wave, whatever is the signal, is going back and forth and back and forth. And so what happens is the speaker now is being pushed back and forth and back and forth and back and forth. The magnetic field is fixed. It's a permanent magnet. That does not change. But what changes is your force on the speaker. And now what is that? That force is IL cross B. And this now shows the clever way which the engineers have managed. What did the engineers manage? They put now a magnet in this orientation. North pole in the middle, South pole on the side. You notice it is a annular magnet. In the middle is North pole, on the side is a South pole, and it is surrounding this North pole. All right. And now you have sent a current because I was speaking, and now there's my speech got translated into electrical signal, and the electrical signal is sending now. At some instant, you have a current flowing, and the current is now flowing. What is this now? In on this side, into the board on this side, out of the board on this side, because I have coiled it, right? So I have now a current now flowing in this wire, and on this part of the coil, the current is into cross B, and B is now upward. You see it? I have I going into the board, and it is cross into this magnetic field up. Therefore, the force is upward. But now how about the other side? The other side, it is now coming out. So the current is now coming out. But over here, the magnetic field is opposite. Over here, it was upward. Over here is downward. So therefore, the force is still upward. So as a result, you have a signal, a current coming in. It is now pushing the speaker out. And then my electrical signal, it sort of oscillates. So it comes out, and then when the current changes the other direction, it goes back in and out and in and out and in and out. That's how you generate a sound. Do you follow it? And it is very directly here. Of course, there will be times when they'll say, I have a current that is so many amps, and then the length of the coil is such and such. What is the force? But that is just applying. The concept that we want is just this. Okay. And indeed, they say, figure it out. And I say it's for engineers. If you like, you can work through it. You say, I have so many coils, and therefore I know the length of the wire is 55 pi, because you know how many coils you make, turns. But those are engineering aspects. But now there is this very interesting. Have you seen this kind of a, it's not a tugboat. What do you say? Have you seen this boat? Yeah, no, I must confess, I haven't seen it either. Oh, you have seen it? No, nobody has seen it. Not really, right? But one day, maybe you'll see it. I don't know where this is. It is not common, at least not in our New York Harbor, or if there is, it's not that many. Most of the other ferries and most of the other tugboats are not of this shape. This is what they call magnetohydrodynamic propulsion. It is fancy. I don't know how much it costs, but it's very fancy. It is making use of this law. What it is here, what it is there is a magnetic field upward that is inside here. They have a magnet, and it's not a it's a big magnet. I mean, strong magnetic field. It is not like just the Earth's magnetic field, a third of a Gauss. I don't know. It must be like a Tesla or 2 Teslas. It is a strong magnetic field. So there is a magnetic field here, and you now have a current flowing. All right. The magnetic field is supplied by the boat. I mean, it's installed in the boat. It's a permanent magnet. And now you put a electric field across so that there's now a current. When you have a current flowing this way, there will now be a force. The force will be in this direction. So you are relying on the magnetic field from your magnet and this current that you supply on the boat to now push your boat forward. You follow? This is what they call MHD, magneto-hydrodynamic propulsion, to push this boat. And now I don't know the engineering numbers. Maybe I should have looked it up, or maybe you may be interested in looking it up. You can then sort of ask, what must be the strength of the magnet? It's clearly stronger than my laptop, whatever my magnets there are in my laptop. These must be so many Teslas. And then you got to have a sort of not a 15-volt battery, like for my whatever car battery, 15 volts. I don't know. This must be a big capacitance with a big electric field, because when you have this electric current that is big, and you now are able to have a magnetic field that is big, you will then have a strong force. And you need a strong force. Why? Because this boat itself, the mass cannot be just 100 kilograms. The boat itself, the mass must be, I don't know, 1,000 or 2,000 kilograms or 5,000 kilograms. So you need a big force to actually have this boat go across to wherever the other side of the shore is. All right. But do you see that it is actually a very cute, sophisticated application of this law? But you have to have sophistication to have a strong enough magnetic field and to have a strong current flowing. All right. And now we have already sort of begun to have a thing about a coil. So we now make use of this and apply it to a coil now. And what we are now saying is, if I have a coil, and I put this coil between two permanent magnets, this one north, this one south, so that the magnetic field is in this direction, the question is, what would my coil do? Right? I mean, that's a easy enough question that you can ask. Based upon this formula, well, we can say there are forces acting on this. And we now look at the forces acting on it. If I look at this, given that this is a current and I know the direction of the current because I hook this to the positive terminal and this side to the negative terminal, so that my current will flow up on this side and down on that side. All right. And so now, if I look at this, I would like to now know the force acting on it. And let's now apply this formula here. I have I, that's up on this side of it, on this side one. On side one, I have the current is this way, and it is, the magnetic field is to the right. So the current is upward. So let me see, I have to have my force. I have to get my fingers right. It is going upward, and the magnetic field is, yeah, okay. It is going upward, yes, upward, and the magnetic field is to the right. So it's going upward and magnetic field to the right. Therefore, the force is into the board on this side. On side one, the current is going upward, the magnetic field is to the right. So the force is into the board on this side. On the opposite side is out of the board. So what happens is it will now twist the coil. You follow what if this were live, I can show you better, but you have to look at side one, and then you say the current is flowing upward, but the magnetic field is to the right, according to this direction, is to the right. So it is upward and to the right. Upward and to the right. Therefore, the force is into the board. And therefore, it will now twist this coil, this loop, this current loop. It will twist this current loop in this direction. And if I keep having it that way, if I keep supplying, it will just keep going. It will keep turning. So I have a toy now, or I have a motor, whatever you want to call it. And in fact, this would be a DC motor, because what I now do is I supply this to my 15-volt battery, and I am continuing to supply a current, positive here and negative there. And this is my magnet that is in the car. That's a permanent magnet. Therefore, I have this coil that keeps turning, and this is what then makes my axle turn. And it makes my axle turn and makes my wheels turn. That's a DC motor. Do you follow now the concept? You follow the concept? Right? It's the concept is actually quite simple, but you just have to play with it. If you look at the other side, side two, somebody what? Yeah, let me now look at side two. I look at side two and I say it was the current was downward, but now the magnetic field is still to the right. So I got to now do it. I got to now do it. I get my fingers, my hands. It's going downward and it has to, yeah, it's downward and it has to go that way. So it is downward. It is downward and it has to point to the right. Therefore, the force is out. Do you follow what I'm doing? For me, it's easier to show that it is on the side one is easier. the current is going upward and the magnetic field is the other way. So therefore my thumb points the direction of the force and the force is into the board. And then all I can say is the current is opposite on the other side. Therefore the force is opposite. Instead of into the board, it's out of the board. That's why it is turning it. And it keeps turning it and keeps turning it. All right, so that is the DC motor. And now you got to give, take your hat off to those automotive engineers, for the people who studied and invented these motors, that this is the basic principle, but what they're able to do is to have gear shift 1, gear shift 2, gear shift 3. They are able to transmit this rotation, right? Because I have now this 15 volt, car battery. It's 15 volts, and it now within my magnetic field, and it is turning and turning and turning and turning and turning. They are able to now transmit that to the 4 wheels of my car, and you notice it was the axle was, along the length of the car, but you got to now separately transmit that to the wheels, which are on the perpendicular. They invented those meshes, meshes, gear meshes, to basically such that when this one turns, the other ones will turn in a certain way. And they have gear, first gear, second gear, third gear, by having different moment of inertia. And I guess you should remember 203 to recall that conservation of angular momentum. All right, I think we have done enough with this. Any questions about this? Because we are going progressively more and more, and then we will come to an even deeper subject. We started with QV cross B. We applied it to I current L cross B. And now we want to say, I have a current loop. Now, what is the torque on it? And then you got to say, gee, that was in 203. Many years ago. Well, not many years ago. Many months ago. It was 203. Do you remember what is torque? Do you remember what is torque? I guess everybody's asleep by now. A little, yeah. I mean, as I keep telling everybody, if you don't remember anything, you better remember torque. Torque is basically, again, a vector. It is F cross D. All right, so now we first start with the law that we know. It is that if I have a current loop, and on this side is coming out, on that side is going in, that's the current loop, and the magnetic field is this direction, that there is a force on my loop. And the force on my loop is that this one is coming out, and it is, the magnetic field is to the right, so it's coming out and it's into the right, so therefore the force is upward. So I have already figured out its force is upward here, and because this, on this side of it, the current is going into the board, is opposite. Therefore, on this current loop, the way it is now, it has a torque on it. You remember from 203? If I have a baton, right? And I am applying a force on this side of it and on this side of it, or let's say I have a bar, a wrench bar, and I want to turn it. If I have a rod that I want to turn it, I will have to apply a torque to turn it. And the maximum torque is where I apply a force here and apply a force there. And that would then give me the maximum torque. If instead it was this way, if my current loop was in this orientation, such that this side, the current is coming up and the force is up, this side, the current is going into the board is down, the net force on this is zero, and there is zero torque. If it is this orientation, zero torque. If it's this orientation, maximum torque. We are now beginning to understand that there is a correlation, that a current loop in the presence of a magnetic field, that it would actually turn it such that the torque is zero. That the fact that you have a magnetic field and this is the coil and you have a steady current, it would want to turn it so that the net torque is zero. And you can now figure out what is the torque. Here is the formula. You have the coil and the torque is the force times the sine of the angle between the coil and this force, and the torque is F d, d being the arm, sine phi. Well, you can therefore figure out the net torque. It is ILB, that's from what we learned before, and it is by this distance, that's your arm, is half of the width of this coil, because that's what it is, sine phi, and when you add the two, it is IAB sine phi. And you can now say that the torque on any coil is, the engineers invent a notation, they call this the magnetic moment of the coil times B sine phi. So they now say that when you have a coil and it has a certain number of, if it's a coil that has so many turns, each one carries a current I. If you carry so many turns, then the net current is Ni. And you now have the area, because the force ILB times the torque involves the arm. So you now have this thing called magnetic moment times the whatever is the external magnetic field sine phi. That the torque on this is proportional to sine phi, and the torque would be zero when the angle phi is exactly zero, which means that the coil is oriented directly in this parallel to the magnetic field. Now you won't be asked for the torque, because for the DC motor we leave it to the engineers. But the concept that I wanted to sort of let us have a firm grasp on is that there is always a force on the coil due to an external magnetic field, and it is that which causes the coil to turn. Well, this is for engineers. You can put in the numbers and work it out. We won't go into this current carrying coil for the CD printer, for the CD, because again, that is basically engineering. But we do want to know, since we mentioned about the DC motor, to get back into this DC motor and then see what was the cute thing, that you indeed have your battery and it now is connected to this where on this side, it's a current that flows up and it comes back down over here and it is connected to the battery. And even when this turns, this will now catch this, so that when it turns, now again it is positive current upward. Are you following this picture? I mean, this is the key central concept involved in the DC motor. When you have it at first this way, the current is positive on this arm, right? And so it begins to turn, right? It begins to turn because the force is IL cross B. So it begins to turn. But then when it turns so that now it is on this side of it, this side 1, which I call side 1, no longer is in contact with this. It is side 2 that is in contact with this. Now when it is now side 2 that's in contact with this, now what we call side 2 now becomes side 1 because it now is going up. So again, it will turn. So it will keep turning. That's the trick. It will keep turning by design. Are you following me here? This is together, right? It's one solid coil, but it is now connected at the base such that this side is in touch with positive, that side is in touch with negative. However, as it now turns because of your force law, IL cross B, one is coming to that side and side 2 is coming to this side. But side 2 now, the base of it now suddenly is in touch with the positive terminal. Whereas side 1, what I call side 1, now suddenly is in touch with negative terminal. Therefore, what was side 2 is no longer down, but the current is up. And since side 2 now is current up, it will now continue turning. And that is the very key concept for the DC motor. So this is just to show you. All right, so we need to sort of get that straight, that the basic thing is this law. There's no name to this law. Later we'll learn the name Ampere's law, but that's not Ampere's law. There's also Biot-Savart's law, but anyway, this is the key thing for our force law. It's actually called Lorentz force for QV cross B, and I don't know if there's a name associated with this law. Okay, now the book wants to call it right-hand rule number 2. That's okay, but what is more important now, so I download this one just so that the focus is not the fact that you call it right-hand rule 1, right-hand rule 2. It's rather, when I have a wire, it actually produces magnetic field. When I have a current flowing in the wire, the previous one, it was, I have a current flowing in a given magnetic field. And this external magnetic field is strong. That's how I'm able to turn things, right? But now we are beginning to focus on the wire itself and say, supposing I don't have a permanent magnet, I only have a wire by itself. I have a wire by itself, and this wire now carries a current. Now, if this wire itself carries a current, it itself will produce a magnetic field. You see now the thing that we are talking about? It itself will produce a magnetic field. And then you can say, which direction? Well, that's where, again, is the right-hand rule. If now your thumb is in the direction of the current, then the magnetic field wraps around this current. So this is the right-hand rule. If your thumb is in the direction of the current flowing, your fingers will give you the magnetic field. Of course, this rule by itself doesn't tell you the magnitude of it, but it gives you the sense of direction. The book calls it right-hand rule number 2, but anyway, it is basically, now you begin to say, if I had a charge, you remember we said that if there's a charge, the charge is a source of electric field, and the electric field radiates from the point charge, Q, and is radial. Now we say, I actually have my current, which are all these electrons or whatever that is moving inside my wire. Now I have a wire carrying a current. It is a source. It is a source of magnetic field. And this magnetic field, instead of radiating outward, instead of, what these electric field are, they radiate. The current that is flowing produces magnetic field wrapped around it. Okay, the current produces a magnetic field that wraps around it. And here is the picture. I have a current flowing upward. It produces magnetic field that's wrapped around it. And this is now a long straight wire. And this is now it's sort of like the Coulomb's law. But now it involves, in these engineering units, mu zero, which is the permeability, is a number. It's a constant. It's called the permeability of free space. And it is 4 pi times 10 to the minus 7, I guess, right, Tesla, in these Tesla units. And it is one where the magnetic field strength is strong when you're close to the wire, and it gets weaker and weaker and weaker and weaker. It's not inverse square law. It is like the potential, electric potential, is 1 over R. All right, so now we begin to say, I have been learning about what is the force on my charge due to an external magnetic field. I have also now learned what is the force on my wire due to an external magnetic field. But we are now getting deeper, and we're saying, but what is the magnetic field that is produced by the current itself? Oh, then there's this law. And you now can say, what is the force? Oh, why is this here? Well, the book, I don't know. I keep following the book, and I am not that happy with the book, the way they do it. But anyway, this is going back to this formula, application, example. And you can now follow what they say and figure out what is the... Yeah, this is going back to what we already have covered. Oh, I see. They say now a current, haha, oh, okay, now I see what their point is. They say that I have a current, and now outside the current, I have a charge. I have a wire that carries a current, but now I have an innocent little guy, Q0, passing by. And you remember, for Coulomb's law, you say, I have a source charge, it produces electric field. And then if you come by, you have no charge, you say, there's no force on me. But if you have your own charge, Q sub 0, you will then feel a force, which is your Q0 times the electric field due to the source charge. Now they're saying, I have a source current. I have a current, I. And now I would like to know, what is the force due to my wire on you who's passing by? You are passing by with some velocity v, and now the force on you due to a magnetic field due to me is qvb, where b is now mu 0 I over 2 pi r times sine theta. All right, so this then is the application. that I now look at this as I have a wire, and now I know the wire itself produces a magnetic field. And then you, innocent guy, you cosmic ray, you whatever, you just passing by on 135th Street, you have a charge Q, and you are moving at a certain velocity, and you pass by me, you will find a force on you. And the force on you now depends on how far you are away from me, and depends on this mu zero. And you can then figure out what is the force. And I think that's about it. I will stop here. Next time we will then go further and say, I have a current, a wire, and I have another wire. What happens? They are now close to one another. What happens? Do they attract or do they repel? And we will figure out the conclusion or the reason for it. Okay, I think this is about. Any questions? I hope I'm not going too fast, have I? Oh, you want to go to the last slide? Yeah, what was the question? Unmute yourself and ask the question if you have. You see, I have a wire. I have a wire that already carries a current I, and it will produce a magnetic field. And you happen to pass by. You have your charge Q, and you will now feel a force due to the magnetic field that is produced by me. So it is now taking your magnetic field due to you, and I am a stranger passing by with charge Q with velocity V, and now there's a force on poor me. And now they want to know, what is the force on poor me due to the fact that I'm coming by a wire? And that's what this is. Okay. Okay, so I think time is up. For those GH3, you have is it recitation or is it lab now this week? I don't know. Recitation. Okay, this week is recitation. All right. I can't keep track of which one is because GH1, GH2, GH3, they all have slightly different schedules. Any other questions or comments? Okay, so I'll see you on next Monday. Okay. All right. So have a good week and finish homework 19. If I give you a little extra grace, I don't know, maybe an extra 1 day or so. I don't know. I will have to look at it, but I'll look at it after dinner. It's getting to be my dinner time. Yeah? Okay. All right. Could we have a little review? Yeah, I will have a sort of a review on Monday so that you know what is covered, but I'm not going to tell you exactly what question is number 1 and number 2. Okay. Okay. All right. If you have questions, you can ask now or. Okay, I will log off now and have a good week ahead. Bye.